All right, everyone. I realized that I didn't go over the neuromuscular blockers, aka the ganglionic blockers. So I thought I would go back through and talk about them. Um, the so think of this as just like an addendum to when we talked about anticholinergic drugs. Remember back when we talked about anticholinergic drugs, the big structure that we're trying to mimic is acetylcholine. And remember that in acetylcholine, we have two big moieties. We have the ester and we have the quaternary ammonium. Because of this, all of our drugs that we're going to look at today have to, in some way, mimic the function of acetylcholine in order to get to the synapse and where acetylcholine takes place. So unlike the cholinergic drugs, which we talked about in the first MedChem exam 2 video, these drugs are going to the nicotinic receptors for skeletal muscle. So let's take a look. The first drugs that we're going to look at are called the ganglionic blockers. If I can spell. These drugs are not used much, if at all. They're very, very old drugs. They did their job when we had them, but we just have better agents now with less side effects. And if you look, the drugs pentylenium, trimethophan, and mecalamine, all of these drugs mimic that structure of acetylcholine, right? Specifically, that they're going to sit in the receptor and prevent the activation of the receptor. So the biggest thing that we care about in terms of these drugs is the space between the nitrogens, or the space, the number of carbons in the structure. So for example, in all of these drugs, so we have N plus or S plus in the case of trimethophan. Same thing with mecalamine. We can easily protonate this amine and end up with N plus. All of these moieties are mimicking mimic. No, one M. Mimic acetylcholine. So you need to have this positive atom in order for it to happen. What you notice is that in between, we have 1, 2, 3, 4, 5 carbons. And what's really, really interesting about these drugs is that this space of about 10 to 12 carbons is the maximum size of the receptor. So a drug that has greater than 10 to 12 carbons would be unable to fit in the active site of the receptor. And what we see in the case of pentylenium, trimethophan, and mecalamine is that each one of these drugs fits within this 10 to 12 range. What we know about other drugs is that actually, as you get closer to this range, you get a better and better fit. But in terms of what you need to know for the drugs provided in this section, just know that having a 5-carbon distance, same thing here. We have 1, 2, actually it would be counted. From, I think it would be that 1, 2, 3. 3-carbon distance. So each one of these is enabling the perfect fit within the receptor. Mecalamine is a little bit special in that it is able to cross into the CNS. What this means is that mecalamine is going to be working on the cholinergic receptors in the CNS, which means that it's almost working similar to a nicotinic drug like varenicline or nicotine itself. And if you compare mecalamine to nicotine, you'd actually see that they're very similar in structure, 3D structure, maybe not 2D structure as we draw them on the screen. The really, really interesting thing about mecalamine to know is that it doesn't sit in the receptor, but is a negative allosteric modulator. So essentially what it is that it's going to decrease nicotinic output. And when you think of the uses of mecalamine, think of it, where would we want to decrease nicotinic stimulation? When someone is using tobacco products, when someone is using nicotine products. So the function of mecalamine is to decrease the output of nicotinic receptors in the CNS. And so the benefit here is to give it to someone who's trying to quit smoking, and so they get less and less benefit from their nicotine over time. It has some significant side effects, so we don't really see it that much anymore. All right. The next ones that we're going to talk about are the neuromuscular blockers. So while these ganglionic blockers are functioning where the two neurons are coming together inside the CNS, the neuromuscular blockers are during that synapse between the neuron and the muscle. So up above, we're talking about synapse to synapse, or preganglionic to postganglionic. Here we're talking about neuron to muscle. And so all of these drugs are going to block the signaling, the very tight signaling between the CNS trying to control our skeletal muscle and the CNS controlling the skeletal muscle and its ability to depolarize and repolarize. So the first two drugs that we're going to look is decamethonium bromide and succinylcholine chloride. What you'll notice, first of all, is decamethonium mimics our structure of pentalinium up above. And it comes from the same family of drugs, except now you can see that we have hit that sweet spot of 10 carbons. So having this 10 carbon moiety allows for a perfect fit in the receptor at the muscle junction. So up here, if you want to get to the ganglion synapse, not good to get towards 10 to 12. Down below, for the muscles, the closer you are to this 10 carbon gap, 10 to 12 carbons, the better fit you have. Succinylcholine, however, is essentially two choline moieties. So here's the first choline, here's the second choline, two choline moieties stuck together. What's really interesting about this is that if you count the spaces, what do you notice? We have the same gap between our N pluses that decamethonium had. So once again, we had that perfect fit in the neuromuscular junction. And what this is going to result in is depolarization without detachment. So in other words, these drugs are going to sit in the receptor and they're going to keep the receptor activated, meaning that it can't repolarize and relax. And so these are what are called the depolarizing neuromuscular blockers. Now, you remember in PCOL that we have some drawbacks to these drugs. Succinylcholine can cause malignant hyperthermia, so not that great. You have to be very, very careful and all that good stuff. Moving along, we have our next group of drugs, which we will start with what's the way to describe it? The curiums. Oops. So we'll take a look at doxycurium, atracurium, and mivacurium. And here is the structure of doxycurium, I believe. Yes. And essentially, these drugs are going to have very, very similar structures. I'm only going to show you one just because they're going to have the same effect, so you can fill these in specifically. But a couple of key features. First of all, you notice that we have this N plus moiety. Let me do this in a different color. We have the N plus moiety that we need in order to act like acetylcholine. Whenever you see a neuromuscular blocker, you should always count the distance between these two positive groups. And what you see is that we have 12 carbons. So we just hit the limit of that perfect fit. So here we occupy the aspartic acid domain in order to get that blocking effect. And what we have all over this drug is a bunch of tetrahydroisoquinolones. So here we have our N plus, instead of just having methyl groups attached, here we have quinolone groups. And the quinolones are going to prevent the initial depolarization. So in other words, the N plus and the distance between them allows it to sit in the receptor, but these giant groups on either side of the N plus prevent depolarization. This is where we get the idea that drugs like doxycurium, atracurium, mivacurium are non-depolarizing. So they sit in the receptor, but they don't activate the receptor. Hopefully that makes sense. Interestingly, instead of having this big floppy chain, like we have in decamethonium, succinyl chloride, in these curium drugs, instead of having this big floppy chain, which don't forget what's in the middle of this group, esters, right? I'll put that in a different color, put it in red. You have these ester groups, which are going to be easy sites of hydrolysis. So you're going to have very, very easy metabolism of these drugs. So what we can do is that instead of relying on this succinylcholine backbone, right? Because you can see how succinylcholine is integrated into the structure of doxycurium, atracurium, and mivacurium, we can use a steroid backbone. So you might remember from organic chemistry that this four fused ring structure is a steroid backbone. Still have our N pluses. So we have N plus, act like acetylcholine. But instead, what we're using is a steroid backbone. This is acting in the same way that the quinolones did, which I'll use a similar color. And first, we should count the distance, which, if we look, oh, look, we're at 8 carbons. Even though it's only 8 carbons, remember that molecules exist as a 3D structure. And so I imagine that these nitrogens in the 3D space are closer to 10 carbons than they are 8 carbons. Or maybe they're just a little bit too close. Who knows? So we have that 8 carbon distance in order to fit into the neuromuscular junction. And then we have that steroid backbone to prevent depolarization, which again, these pancuronium, vecuronium, pipocuronium, rocuronium, they are all non-depolarizing neuromuscular blockers as well. What is the difference? In the main structure, we're using a steroid, which in all intents and purposes is going to be very, very lipophilic. But again, are these drugs going to be less metabolized? Not really, because once again, what do you have hidden in the structure? Bunch of esters. In general, though, the curoniums have a longer half-life than the curiums. The reason for that is that if you break this internal ester, you completely get rid of the drug. But if you break one of these external esters, the distance between the N plus doesn't change. So all of your curoniums are longer acting than your curiums, purely because you don't destroy the drug if you remove an ester. Remove an ester. So hopefully that makes sense. If you have any questions, please let me know. And that should be, I think, just about everything we need for the exam. All right. Good luck.